Talk to you guys about a project that we just launched at GTC EU, which is one of our GPU technology conferences. We did that earlier this month. So this is an open source project called RAPIDS, and it's how we're helping to accelerate data science. There's a lot of content here. I've also got a live demo. The projector's a little wonky, so I'm doing the best I can here. If there's things that are hard to see, let me know, but let's try to do all the questions towards the end. So as anyone knows that is doing data science, there's a lot of challenges. Namely, I mean, there's just a few to name off here, but like interoperability, feature engineering, and data ingest is kind of expensive. Experimentation speed is key, and I'll highlight that in a second. And then also the increase of the amount of data that is available. We kind of went through this period back in 2012 and 2013, and then all the way to, like, even with some companies still today, of let's just capture everything, throw it into a data lake, and we'll sample it. But as everything grows, that trend of sampling just kept going, right? Like, we're just going to take this little piece of sample, or even though we have years of data, we can only process it like a week at a time or something like that. And really with RAPIDS, what we're trying to do is to break that and actually be able to say, let's look at the entire data set and do it very quickly. So what happens when you usually kind of like fire off a job, right? You're like, oh, time to go get a coffee. It's going to run maybe overnight, maybe for a week. There was one retailer I was working with that's like, yeah, we run this job, and it's 7 days like to run for us to do 1 week of processing. And for those of you that are Futurama like addicts, that's the episode of the 300 Big Ones. So one of my colleagues that I work with, Alan Enemark, it's at exactly Alan. He made this awesome chart. I know it's really blurry for you guys. Definitely look at the video that's going to be posted online. It's going to be like full high res. I apologize about this. But on the CPU-powered side, basically, let me see if I can actually maybe make this a little bit bigger. We'll just do it old school. A little too much. Yeah, one step back up. Sorry, apologize. All right, so like on the CPU-powered workflow, you kind of start at 9 in the morning. You're configuring your ETL workflow. You start the workflow. You get a coffee. It's still running. You get another coffee. Green here is while your data is running, or your ETL process and stuff is running, or while you're training. Red is the time that you're actually working. Then another one past noon, and crap, you forgot to add a feature. So you go ahead, restart the ETL workflow. Eventually you have to realize you're switching to decaf. And then you find a bunch of unexpected null values stored as a string, start it again, and then it goes into pass. And the one thing that's cut off down here is the stay late. So really what we're trying to do is kind of change this paradigm. So with the GPU-powered workflow, it's more of, you get it in 9, you configure it, you start it, and then it's done. And then you can play with it again. And so this is where we start being able to do these, narrow down that time it takes to get that experimentation and get those results back. And then, even when you run into the same problems of saying you forgot to add the feature, you ran into, null values and streams, like the penalty there is not as high as it was on the CPU side. So we can keep going through and then quickly move from the ETL process, because a lot of times, 80% of the work sometimes in doing what you need to is the ETL process. Everything else, the training, and those are kind of known. It's getting everything, your data, specifically into those algorithms, and so they will work. It takes most of the amount of time. And the one thing that gets cut off here, which is actually, important for everybody in this room, is go home on time. All right. Oops. And my bad. So if we think about what the kind of de facto data science platform is on the CPU side that I was talking about before, you've got Python, Pandas, sklearn, and then NumPy. And one of the things that we can do is, not to worry about with the interoperability issues that I talked about previously, is to use Dask. Dask is Python, allows you to go through and scale these workloads very quickly and almost effortlessly, because you don't really have to say, oh, now I have to change everything for this new framework or this new technology. But if we think about where we've kind of come from, I mentioned Hadoop before. There's like kind of where we started at the top of being Hadoop, where we're doing queries, ETL, and machine learning trained on these very large clusters, thousands of nodes, if not tens of thousands. And it takes a very long time. So if you think about the width of the slide, or the y-axis, or sorry, x-axis as being time, then like it takes pretty like the full slide length. Now, when we think about like Spark, we started getting like magnitudes of improvement, 25 to 100x. We got a couple benefits. Less code, language flexibility. Instead of just everything being in Java, you can now do stuff with Python, with PySpark. And then also, it's primarily in memory. So these complicated and expensive reads and writes to disk no longer happened. But one of the things that we start running into on the CPU side is there's only so much scaling that you can do. That retailer I was talking about, they train on a 4,000 node Spark cluster. And it still takes them a week to do that. Because even though the data set is so large, you can only parallelize it so much, and then you start running into problems with networking, disk, like all these other limitations that when you scale out to that part, you start seeing in the graph where what that says is 5 CPUs, 10, 15, 20, 25, and then there's one box with 4 GPUs down there. So you can kind of see the difference that even though I'm scaling up the number of CPUs, the performance of just a box with 4 GPUs in it is much better. So speaking of GPUs, for the win, right? We're just going to put some GPUs in there. Everything's going to be different, just like Krusty adding some speed holes to his car. The problem here, though, we didn't get the same speed up that we thought we were going to get. We got 5 to 10x. And one of the reasons why we were having that is because if you think about query, the ETL process, and the machine learning process, each one of those was a different GPU package or a different application, and that had a different format for storing memory on the GPU than the next one. So anytime you went from the next stage, you had to copy and convert out through the CPU, which is expensive and takes a very long time. And that's where you start seeing these CPU write in those dark boxes there, where we start getting that penalty hit. And the challenging thing that we saw about a year ago with this and led us to the initial project called GPU Open Analytics Initiative was we needed a common data frame to be able to hand data back and forth between all these GPU processes. And then depending on the workflow, a lot of, some of these things were so quick on the GPU, but it was so expensive to do that copy and convert that 80% of your entire time would be spent doing that. So obviously we were like, we need to be able to do better. So good news, everyone, right? If anyone is looking for a class RAPIDS, it doesn't actually exist. It's just me being funny. But that's where RAPIDS comes in. So Rapid Accelerated Platform Integrating Data Science. So one of the things that we wanted to be able to do was not actually go through and just say, OK, great, we've got GPUs, throw out all your old code, come over to my platform, and build it all brand new again. Trust me, I've also done cybersecurity research in the past and trying to talk to anybody that has spent lots of millions of dollars on hardware, software. You tell them that, and it's not going to fly. Same thing with developers. So this was our approach of saying, OK, how can we open source something back to the community, but also make it that it's workable for you guys without having to have this large overhead of being able, of having to redesign everything that you've already done. So where does kind of RAPIDS sit? We talked about the CPU, kind of dev stack, and this is the GPU one. So at the top, we've got Python. Off to the side, the deep learning frameworks. The things that are in green are what RAPIDS is currently working for. It's kind of hard to see, but the small box on the right, cuDNN. RAPIDS is this one big piece here where it is comprised of cuDF, which is the data frame piece that I mentioned before, cuML, the machine learning piece, cuGraph, so graph operations. All of that sits on top of CUDA, which allows that interface to the GPUs to do a lot of these functions. And then we're flanked by Dask and Arrow. So Apache Arrow is one of the projects that is here on the left. They also saw this from the CPU side. Like if you're thinking about big data space, I'm in Spark, I need to go to Hive. I'm in HBase, wherever I need to go, there's a copy convert there too. Also goes through the CPU, also takes a long time because everyone stores things just a little bit differently. And Arrow was this initiative to say, OK,
how can we actually all speak the same language? How can we have the same metadata around things and then be able to do these types of operations in memory so we can pass these pointers around? And that's where the GPU data frame comes in. And our goal through the process, and a lot of these, some of these features have already actually been incorporated into Apache Arrow since 0.7, I want to say, where we're actually going through and the data frame features that are uniquely specific for GPUs are actually being integrated back into Apache Arrow. But they are compatible, so then it starts opening up even this larger ecosystem where if you did have, like a big data big data setup, and you've got Hive and Spark, and I think Spark, it's 2.3 something, where they started doing full Arrow support, where you can now export these Arrow and then bring it in with RAPIDS, digest it, and then start doing machine learning and training, and then digest out or send back out an Arrow data frame. So this now starts being able to be like the glue that was missing between all these different applications. So now where does that get us? We've gone through the lineage. Now we're down towards the bottom where now we're seeing that magnitude and more speed up improvement. So now we're getting to the point where we have the same code. There's minor changes and that kind of stuff to it. We're starting to do language flexible. This has mostly all been written for Python first. However, the underpinnings for the data frame and that kind of stuff are actually C modules. So there is no reason why if somebody's in here is like, I'm a huge advocate of R, you can always fork off of that and start adding the same R bindings that we've done with Python to expose the same primitives and functions. And now, the last part there is we're primarily on GPU. So instead of this being a situation where, I'm on GPU for this part, and then I have to hop off and hop back on, now all my operations are there because once the data is queried, I can just hand the pointer off to my ETL. ETL does what it needs to do, hands that pointer off to the machine learning, and I'm able to do the machine learning all without leaving the GPU. So how does that kind of compare in a side-by-side? So on the left-hand side, we've got kind of what the Spark ecosystem is. And then on the right side is the RAPIDS GPU ecosystem, where it's similar layers like I talked about before. Over here, we've got RAPIDS primitives, some of the arrays and stuff that I will talk about in a little bit, and the connectors. Sitting on top of that is QDF, QML, and QGraph. That allows us to be able to do those different operations. And you see the similar things on the Spark side. So like Spark, they have MLlib, they've got GraphX, and then also stuff to be able to manipulate data frames themselves. And one of the points here is more cores, higher bandwidth, because you can actually see 20 cores for a CPU, 128 gigabytes a second per CPU, versus we're at 900 gigabytes a second per GPU. And 5,120 CUDA cores. So the whole thing here is about trying to parallelize and process data faster and as fast as possible. So let's take a deep dive, because I know somebody's asking, would you like to know more? So RAPIDS open source software, how does it also kind of look? The GPU memory interacting with Apache Arrow is kind of like the base layer. We've got these different pieces that I've talked about. QDF is more around the analytics. So even though we are integrating with Apache Arrow, there are going to be certain things that Apache Arrow doesn't support, right? Like Apache Arrow is great for defining metadata and saying this is what my data looks like. There are going to be some operations that we're going to want to do on the GPU and wholly own, which is why we're still going to have QDF as a piece, even though the functions and that kind of stuff might eventually migrate into Apache Arrow, which is the plan. There's still going to be a subset of joins and group bys and filters and all the kind of stuff that us handling the logic and being able to do it for the GPUs will be much faster and more efficient. And then QML is some standard machine learning. I've got a couple of examples I can show you of the 3 that are available today. Machine learning algorithms that we're actually able to integrate with QDF. So then if you're able to get the information into a GPU data frame and you're using QDF, then you're able to use QML to actually be able to process that. So that completes that chain that we were looking at before of query, ETL, and then the machine learning train. cuGraph is not available yet. It's in the process of being open source, but it's a similar thing of saying, okay, we've got graph, we want to be able to do this on GPUs, we want to do it faster, but also baking into the GPU data frame, how do you represent graph data in a CSR method or compressed sparse row method. We're working with PyTorch and Chainer on the deep learning side, and then on one of the visualizations that if you want to check it out, there was a visualization that was done at G2C EU for the keynote that was done by also Alan, who did the kind of the data scientist sketch using Kepler, and all of that on the back end was talking to Arrow and using the GPU data frame with all the data in the GPU, so you could actually visualize much more data than you would have otherwise just on the CPU. And what we're trying to do is like kind of this loop of data preparation, model training, visualization, and then come back, right? So visualizations only get better by actually going through and like you start off with a basic visualization, come back through, and this iterative cycle is what actually gets you to the results, or kind of like the aha moments. And by narrowing down the time, the experimentation time that you need to be able to go through the prep and the training process, you can actually make that loop much faster. It's succinct. So talked about the data processing engine, so specifically about QDF. There's a lot of key features and stuff on there. I'm not going to like read off of all of them, but there's a lot of stuff that we're doing where we can actually do things faster than Spark with a single V100 GPU, which are available on cloud providers. And then just being able, like I said, some of the things that I think were really interesting is what we're trying to do, I'll touch more on, is like input-output formats too. So a lot of us deal with CSV data. There's actually a GPU-based CSV reader, which is super fast, just because that tends to be a lot of the data formats. And we're also working on Parquet and ORC integration as well. So we haven't kind of gotten to like the rest of that list as far as standard formats, but it is coming. And QDF, like I mentioned in the previous slide, is directly integrated with QArrow and QGraph, and then also QML. So there's not necessarily like where you have to go through and install it multiple times. As long as QDF is already there, you can then use QML, no problem. So how did this kind of integrate with some of the other things? One of the things that we also looked at was is this number array interface. So there's actually a CUDA number array interface that we're supporting. And what this allows us to do is like that way there's one array interface and there's not, I think at the time we were looking at it, there was over 14 for the Python community. I've got the polls later in one of the other slides, but I think like PyTorch and a couple other places have already started like integrating that as kind of the de facto based off of what Numba's been doing. And that's full integration with QDF, QML, and QGraph. So that way this also goes to that whole penalty thing of I have something in this number array interface, and I don't want to then have to like pay for the penalty to convert back and forth. And then lastly, as I mentioned before, Dask, being able to scale this out. So what we've done with one of the demos that I've got later is we're actually using Dask to actually scale out across multiple. So it's on the same node, but there are 8 GPUs on that node, and we can use Dask to basically individually address each GPU and then run these different workloads to be able to kind of scale out. So what is Dask and why is RAPIDS using it for scale out? So for those of you that haven't used Dask, it's great. Matt Rockland and the others that have contributed to it for Dask, I think they've made an amazing product. For us, it was really made sense to kind of go back to the whole interop part. We didn't want to have to build our own scheduler to say, oh, you want to operate on CUDA and GPUs, use our CUDA scheduler or whatever it is. By integrating with Dask, then it makes it super easy that basically we just import GDF or QDF into with the notebook that we're using, import the stuff that we need for Dask, and then we're able to run without anything else there. And so the nice thing I kind of hinted to is like you can run multiple Dask workers per node to allow for the easier development model. like it scales to however many GPUs you have on that particular one. Because a lot of times when you're thinking about it, it's like, you might be single node, single GPU, single node, and then might get a little scared about this whole like, all right, I need to transition to multi-node, multi-GPU. Dask allows you to do that very easily without having to really refactor your code base as well. So as long as it runs on Dask, one GPU, generally it'll then easily scale to multiple GPU, single node, and then multiple node, multiple GPU. So basically, like there's the QDF primitive. So there is a little bit of, there's Dask GDF this repo that's on GitHub right now. That one is our implementation that we're using of Dask. It's just our fork at the moment. Eventually this will be baked in. We're working with Matt Rocklin and others at Anaconda to make this as community friendly as possible. And one of the nice, awesome parts about this is the demo that I want to show you later is Dask will also, especially with this version of the Dask GDF, it will handle what's called RDMA. So like what that allows you to do is over InfiniBand or over RockE, like within the same node, you can actually bypass the CPU entirely. Usually when you're trying to use a network interface or whatever to exchange between nodes, you still have to go through CPU. With RDMA, what you're allowed to do is have direct connection between the GPUs, and then that's over InfiniBand or 100 gigabit Ethernet. And that's really where a lot of the, as we start scaling up and scaling out, that's where a lot of the performance gains are shown. And then same thing with QML. So obviously, having something for RDMA and being able to move data, like when you're doing training, is going to be great. But it handles a lot of this stuff under the hood that you don't want to really pay attention to. There's initializing nickel and like all these other things, trying to get like the environment created. The Dask GDF environment, like that handles that for you, so you don't have to worry about all the nitty gritty there. And an example that's up here is just like how the Dask XGBoost, so being able to run XGBoost in Dask, which I'll show you guys later, uses this and doesn't have to do all of that setup manually of tweaking everything. So, we talked about QDF, talked about QML. Kind of where does it stand, like as far as like AI libraries? For like machine learning, there's QML. There's 3 that are out there right now, but there's kind of a list that we're targeting. That being decision trees, random forest, linear regressions, logistic regressions, k-means, k-nearest neighbor, dbScan, Kalman filtering, principal components, single value decomposition, and Bayesian inferencing. I know at least 3 of these are definitely done, and I think there's maybe 1 or 2 that are also on that list. And I can show you the link to that repository. The next part is for like graph analysis, is PageRank, breadth first search, Jaccard similarity, single source shortest path, triangle counting, and Levin modularity. So those are like the ones that are going to be in cuGraph. I know PageRank is implemented now. Not sure on the status on the other ones at the moment. But how is this like really impacting, or how does like cuGraph actually impact is, I don't know if anybody's familiar with NVGraph. That's kind of something that's been released by in a CUDA toolkit to say, here, this is some primitives like being able to do k-means, PageRank, a couple other algorithms while using CUDA. There's also Gunrock. Gunrock is great because it has a very wide breadth of like algorithms. However, it is constrained to a single node. And then Hornet is a different paradigm from Georgia Tech, where it's actually the opposite way. It's really good for dynamic graphs. So Gunrock is really good for single node static graphs. Hornet is really good for like large scale dynamic graphs where you can do millions and updates a second. So we're trying to combine all of the work that's been done with all of these other libraries and pull them into cuGraph, not necessarily that we want to replicate them, but it's mainly for the data side. So can we be able to have a GPU data frame that then we can share, be able to get it into the rest of the pipeline, use it with QML, use it with all the other ones, and QDF, without having to like necessarily go in to the other three. And same thing with transforms, adding the transforms function to different utilities. So how ludicrous, right? So it's got some benchmarks, QDF and XGBoost. So this is just in GPU processing. It starts with 5 nodes of Spark, 10, 15, 20, 25, and then 4 V100, 32 gig GPUs. So it's all in seconds. And the number that's actually called out, so like it's in seconds, but the number that's called out at the top is just the XGBoost portion. So forget the data prep, the ML transfer, and the other parts that are down there. If we just look at the processing speed, we've got 1,400 seconds, which is, I want to say like blanking on that one, but like less than a minute, 55 seconds versus 1,400. Like 23 minutes between the two, and then the other one is 10 minutes between a minute. So obviously this allows us to do this full end-to-end pipeline where we're prepping the data, doing whatever we need to on this 35 gig data set. And it allows us to, you can see the, kind of like you mentioned before, the CPU kind of tails off as you start trying to scale this out further. And then on a single node, you can do it very quickly. But where does that stand for out-of-core stuff? What I mean by this is sometimes when you do, like for XGBoost processing, like there's just so much data, we can't fit all of it into a GPU memory all at one time, right? So what happens is, and this is the demo I'm going to show you guys in a little bit, is it'll actually go through and it processes and does all the ETL and then pushes it to system RAM and then pulls it back in to then do the XGBoost back into the GPU memory to then get it. So the GPU results are stored in the system RAM and then read back in the GPU RAM. And this is done with Dask, and Dask automatically handles this, which is nice. So instead of us having to kind of build this memory manager, Dask has that taken care of. And we can still see like at the top, it's 20, 50, 100 CPU nodes. And then for a DGX2, it's like just really tiny. And this is all, again, in seconds, so we can see, like, again, that turnaround time for experimentation. And then, as I mentioned, scaling out. The other part is like DGX2 to 5 DGX1s. So these are just boxes. DGX2 has 16 GPUs in it. DGX1 has 8 GPUs in it. And we can still see that we can actually get even a little bit more speed up. I think it's like over 10 minutes, and then it's just a few minutes quicker by doing XGBoost. But same format, right? We can't fit it all inside the GPUs, stored in system memory, and then bring it back in a kind of like a staged approach. So just general XGBoost, we have this accelerated, and we're pushing the changes to the XGBoost library in PRs. So the blue line that's at the bottom, and then the other kind of lines that are over here. These are different types of GPUs, but we can see that this continuing trend, 10 to 25x GPU versus CPU performance, strong scaling versus CPU scaling plateau, and then improved accuracy over the CPU multi-node, where there's some data sets and that kind of stuff with CPU we weren't able to run, but in GPU we were able to not only get it done faster, but also have better accuracy. That's just a blow up of the previous one. So what is the speed up for QML comparison to scikit-learn? One of the things here, so there's 3 models. Again, it's hard to see. TSVD is the first one here. So let me see if I can make it a little bigger. Maybe. Yeah, so as the number of samples increase, we can see the speed up that happens for the number of features that we're doing with QML versus the same benchmarks being run on sklearn. We can see the same thing for PCA. and dbScan. And then also cuGraph, so PageRank being run on the GDF graph, so now we're not doing the copy and converts. We're able to actually look at use the data, keep it in GPU RAM, and we're getting these massive speedups compared to the NetworkX benchmark that was done. I'm not sure when. I can ask my team for that if anybody's interested. So amazing. How can I get started, right? So mentioned the QDF. So this is really where the kind of home base would be. Stuff as unary, binary operations, joins, merges, group-wise, filters, UDFs, and then accelerated file readers like the GPU CSV reader that I mentioned earlier. That's all living in QDF. Just a quick heads up. Today, right now, it's kind of, since we did the announcement at GTC EU last week, or 2 weeks ago, before it was in two projects called libGDF and PyGDF that were in GPU Open Analytics Initiative. Those got merged over, or moved over to RAPIDS AI project, since that's the continuing project to go forth. If you did want to check out today and start working with QDF, it's QDF-alpha. There is a dotted line between the two because they're still separate. libGDF is the C underpinnings where you're wanting to build extensions and that kind of stuff, and PyGDF is all the Python facing. So coming soon. I'm not sure why that didn't render, but anyway, that was supposed to be a pray for GitHub because GitHub's not doing too well today. But sometime this week, our plan is to freeze libGDF and PyGDF for the merge. So both of these libraries come together into QDF, so it's one repository, one build process. Everything that we've been doing is on Conda environments, so you can do Conda environment install and also just make it a lot easier to try to build. And Conda packages are coming hopefully by the end of this week of the new QDF that's kind of unified. So what does this kind of look like? Let me think. So we said pandas-like API, you import the PyGDF, and this would actually be QDF soon. And then, how do I go next? Oh, I guess I'm gonna, sorry. So now we have, you can easily convert from a pandas data frame back to a GPU data frame. Sorry. All right. So it's like a one-line operation for you, just PyGDF.dataframe from pandas. So if you've already have a process where you're bringing in data in through pandas, you don't necessarily need to change that. You could start here at this point and get started immediately. So now that you can use all the data, what do you do with it, right? So with the live demo, hopefully it works. Basically, I'm going to run through it real quick, and I'm just going to kick it off. Just a Jupyter notebook that I'm running. Let me go back up to the top. So my imports and that kind of stuff aren't necessarily anything gnarly. I'm importing PyGDF. I'm importing data frames, so I can call that and use that. I've got some stuff that I'm importing -GDF that it gives us that extensions, and I'm just using this kind of start Dask helper script to kind of dispatch the workers, and I can see that there's the scheduler and then the different workers. And this is running on a DGX1 that has 8 GPUs. So if I go to the status page, I think I just have to restart it. So you can see that it's live working on it. Right now, all these green bars are the actual whole ETL process that's being done. This is on 7 years of data, if I'm not mistaken, loan performance data. So we can see we're getting up to 200 and some gigabytes that is being offloaded after we've done the initial ETL process. But even if I inspect some of these, the individual processes for that work were 7 seconds, 8 seconds. And it's just crazy fast to think about in that time. If I go look at that, I'm actually going through here and I'm GPU loading the acquisition data, I'm GPU loading the performance data, I'm normalizing columns and names and that kind of stuff and saying, even though there's low names that are all over the place, I want to change those and normalize it. And then also getting all the performance data. And here I'm actually creating some new features where I want to actually see, did the loans go delinquent? Because with that information, then I can actually start training my model to then predict, like, is this loan that's at risk or not? So let's check back in. So now that we've gotten to this part, and there's kind of like a little stop. So right now I've just done all of the query as far as I loaded all the data in GPU from CSV, 7 years, like 200 some gigabytes, 100 some gigabytes, like 150, 200 gigabytes of data, CSV data, loaded all of that, processed it, did all the ETL work, did all the name transformations, future engineering everything I wanted to. And now at the point that I'm at now, it's all doing the train. It's doing the machine learning model of XGBoost, and that will take like about 2 minutes. So I'll let that run while we go back and finish this. So there's a Docker container out there right now. You can do docker pull rapids AI / rapids AI latest. It has 2 years of the loan data in it, the acquisition and performance data. It has the notebooks in there, one of the ones I just ran, and the pre-built libraries. So like you don't have to necessarily worry about, oh, let me compile libGDF, PyGDF, and everything else. Right now it's limited to CUDA 9.2 plus. So if your host has 9.2 or 10, you're fine. But inside the container, it's 9.2. Updates by the end of the week is more CUDA support, like more different versions and more data sets. So the plan is 1, 2, 4, 8, 16, and 17 years. So if you really wanted to like push it out or scale it out, you could. It's already in use by some other people's. This is one guy, John Murray. He's using it, do some cool stuff with some of the transformations and things that he's doing, all using Notebook and then being able to visualize it. So what else are we working on real quick to wrap it up? So the GPU data frame, so performance and functionality on the single GPU, single node, multi-GPU, multi-node, multi-GPU. String support is coming, so QString. Their support, there's a lot of string stuff that like, even just the renaming and stuff that I did there, and trying it like without having the string support, it's really sluggish and to try to do in pandas. So we've actually are writing a GPU accelerated string manipulation library that allows you to do a lot of the same things, and I'll talk about that in a second. I alluded to it earlier as far as the accelerated data loading. CSV, for GPU CSV is in, Parquet is on its way, Orc is to start. So what is QString and like how does it impact me? One of the things there is like, what about to lower, to find, to slice and stuff like that. You can see these speed ups here and it's just like incredible to be able to do that versus like sitting there toiling row by row trying to do this. And then also here's the CSV reader where basically it's over 10% speed improvement, or sorry, over 10x speed improvement over pandas. The Parquet reader is a work in progress. So that's hopefully will get merged soon. If not, it'll get merged then. And then I mentioned this before. So Python CUDA array interface. So this is where we're trying to standardize around what Numba has been what Numba's been doing as far as the CUDA array interface. Met with them, talked with Anaconda teams, and this is the best way for us to like support you guys in the community without coming in and being like, here's another interface. So I guess we got to get started. And as we went there, I definitely want to go home on time. So that's one of the things that I'm excited about, being able to do this workflow. And here's some links to what we can, as far as Apache Arrow, Rapids, and GPU Open Analytics Initiative. Last one is just if anyone's interested, we are hiring. I'll go back to the other one real quick. So if data scientists, data engineers, interns, whatever, we'd happy to help. or have you on our team. I'd like to say this is like one of the first huge open source projects that NVIDIA has done. So that's why we also want involvement from the community, and we also just want feedback, just because typically that's not what we're known for. But that was one of the things that was very important to myself and the team that I'm on, was to make sure that this is open source so we can actually get it adopted by everyone. And with that, so I'll just leave that there. All right.